hear me? Not yet, I guess. I'll wait. Hi. All right, so we are on. Let's give it 2 more minutes for more people to come up, and then we'll start. All right, so let's go a little bit over what we've done last time and then pick up from there and uh, complete the memory management part and then move to file systems. So last time we analyzed what we do with the memory. If we are to write a little operating system of our own, how would we manage memory? And the first question that we asked last time was, if I have to run a program, basically turning it into a process, where am I gonna load it into memory? How am I gonna do it? And we went through a sequence from the very simple to the current ways of doing it, from single tasking systems where you can only have one program at a time. We improved to having more than one program process at a time. Then we improved to not being limited in size or number. Then we solved fragmentation, and slowly we reached to segmented page segmented allocation, which is kind of close to what's today. Although nowadays it's rare that you'll see segments. Mostly you'll have one segment and segmented pages. Okay. The second aspect that we asked was, how much of a program should we load into memory when we start it up? Options would be load the whole thing or load every page as is necessary. One was wasting memory and it was a slow start. The other was a quick start, but and no wasted memory, but then it would run a little slower because it would keep having to wait for pages to come from the disk. So then we settled for a compromise, which statistically is actually very good. We rely on the principle of locality, and whenever a page is requested, we also load some of the neighboring pages, which statistically are very likely to be required by the process soon. The next question we asked was, all right, now we know how we lay out the program in memory. We know when we load and how much. What do we do when the memory is full? How do we deal with that? And the question was, how do we choose a page to move to swap? That was basically it. All physical pages in the memory are occupied, but we need more memory. So we need to select some victims and move them to swap. How do we do that? And we chose some algorithms for doing that, some predictive algorithms that try to figure out what pages will not really be necessary in the future. Because then moving them to swap will not really impact the performance of our system, of the processes running in our system. And one way was to do this not recently used, algorithm where you would mark each page with 2 bits. 1 bit would be set to 1 if the page is read, the other if the page is written, and then periodically they would both be reset to 0. So then when you need to choose a victim, you have 4 classes of pages: not read and not written, read, written, and both, right? And then you choose from the categories based on which one is most likely not to be necessary. So the next another approach, which I left for today, is to go FIFO. Basically, whatever page comes to memory first should also go first out to swap. This is not exactly great if you do FIFO in this way, because you're not going to know much. You can have a very old page, but very popular, and then sending it to the swap just because it has been loaded first, regardless of how popular it is, will not really yield good results. However, mixing this FIFO approach with the not recently used will give you a somewhat better performance, because we here have 4 classes of pages, right? But the memory has lots of physical pages. So whenever we need to choose a victim, we'll have lots of pages in the same class. So then choosing one from within the same class, that's where we could benefit from using FIFO. Right, so in a mix with NRU, it would work better. And the last algorithm that we talked about is the least recently used, which basically tries to quantify how popular was the page recently. And we had this matrix with the rule of setting the line to ones and the column to zeros every time a page is used, and then always choosing a victim from the pages with the minimum line sum. And with this, we are done with the discussion on what to do when the memory is full. Now, the last piece that I want to talk about regarding memory allocation is basically about what do you do? How do you implement a malloc? So I'm moving inside the process, right? As of now, up until now, we were at system level. What do we do with the process pages? But now we're inside the process. And the question is, how do you represent the memory inside the process? Because the process may want to allocate memory, right? Where would it be allocated? How do you keep track of free memory versus allocated memory? How do you do that? How do you implement a malloc? So if you guys could come up with some suggestions about this, you could frame the problem really simple. You're given a buffer of bytes, and you're required to implement a malloc, which will say, give me so many bytes. And then you have to figure out where in that buffer you should put this allocation and how to keep track of what is free and what is occupied, and so on. Please come up with suggestions. I'll wait a few seconds to see. All right, I'll go on this though, if you guys have no suggestions. The problem is that okay, so present, fine. You go at the beginning of the buffer, search for a place with n bytes free. But the question is, how do you represent a place with n bytes free? How do we search for it? How do we know the bytes are free or not? So the problem is a little tricky because all the memory we have is this buffer. We cannot have structures outside it. This buffer has to contain the accounting of the free and occupied memory and also the data. So then one suggestion would be to organize this buffer as two linked lists. One with free areas and one with occupied areas. And we keep these list links in the buffer. So practically, each element of a list will start with two numbers and then a bunch of data. So an element in our lists will be pointer to the next, length of the data, and the data. So initially, our whole memory will be just one of these, with no following pointer, right? Initially, the whole memory is free, so there is no next. And the length will be the length of the entire free memory, save for these two positions. Let's see. We have, I don't know how to read that, Irelia, I'll say. We have to store in some external data structure. Well, this is the trick. You can't really store in an external data structure because you don't have external memory. This is your memory. So you have to manage in it everything. Accounting and data. So that's why I'm saying this. If you want, we can draw it like this. So let me see how I can do this with my ASCII art skills, which are not really that great. So initially, you can imagine that your memory will be something like this. This will be, let's say, nothing. There will be no initial, there will be no next, right? And this will be length n. And then, let me put some underscores here. And then this is your whole memory. Okay? Extra hardware just for that. What do you mean extra hardware just for that? We're talking about malloc in a process. How would you add extra hardware just for a process? And what if you have many processes? How large should the accounting area be? So now that, let's say we allocate and deallocate our memory at a point, let me make this a little smaller, like this. Our memory will end up looking something like this. And this will be the occupied memory. This will be the free memory. And this will be, again, occupied memory. And let's say, like, I'm not really consistent here with the size. Let me make this consistent. All right, so practically you'll have two lists. Each of them will have a head. And you'll have here the lengths A, B, C, and D, right? So these are the lengths of the data, and then you'll have here the nexts. This guy will have no next because it's the last in the list. This one also will not have any next, and this one will have as next, let's say, a pointer P, and this one will have a pointer Q. Okay, so this is how you would store it. Well, yeah, you could do separate RAM. I get what you mean right now. I'm answering to AutoRedict right now. You could think of some kind of a map. You can have a bitmap marking what's taken and what's not. But I'm suggesting that storing things like this may be more flexible. So now you just have these links lists, and suppose you you get an allocation happening here, then it will look something as follows. This piece will become allocated now. Hold on. Right, you allocate this much, and then you create another area with, so this guy will point maybe to some kind of R, this guy will point to nothing, and this will have a length of F, and this will have a length of E, right? So that's how you allocate, you could allocate space. It would be probably a little better than having a map, but you could go with a map as well. For now, I would like to stay with this structure because the algorithms that we will discuss will be the same, even if you use a map. So now the question that follows is, fine, so we have a way of keeping track of what's occupied and what's not, what's available, right, and what's allocated. How do we choose a free spot for an allocation request? Which one should we choose? I will have a sequence of free memory areas. I get a request to allocate n. Which of the free ones am I gonna choose? So there are a number of ways of going about it. So let's look at them and analyze them. The simplest way would be to just iterate through the free space list and stop at the first spot that you get, at the first slot, large enough to contain your allocation request. So this would be really fast because you don't really do more than necessary. You search first, that's large enough, you use it. The trick that will happen here, though, is the fragmentation. You keep doing this, you'll end up with really small pieces of free memory. Like you can see here, now you have this and this, right? Together they would make much more, but they are split. And you don't have paging in here. So you would really have to rearrange memory if you want more. So if you do this, if you take the approach of the first fit, you don't really address in any way fragmentation. You're at the mercy of chance. Now, I really suggest, well, why not try the best fit? This is a pretty neat trap. Best fit sounds very intuitive. How about we search the whole list for the slot that fits our request best? You know, closest fit, best fit. For this, we could even arrange our list in increasing order of you know, by size. So then searching would not be that bad. You just go and the first one you'd find would be the best fit. However, you'd have a little more processing after allocation. You have to rewire the list to still be order. However, when you do best fit, you're going to be left with really tiny slices of free memory. You'll never find something, well, you will, but rarely find something that fits perfectly over the request. And being left with really tiny slivers of memory in which basically nothing will fit is not that great. So this actually points us to take the other approach, the one that's not that intuitive. You could go worst fit. Always choose the largest chunk of free memory and allocate there, because that will leave behind a large chunk of free memory, thus impacting fragmentation in a different way. You can delay fragmentation because you're not leaving small things behind, you're leaving large chunks behind. So that is, as the name says, the worst fit approach. For this one, you would have to arrange your lists in the increasing order of the free space zones, so that you can basically, you'll always take the first. So it's gonna be fast, but you also need a little more processing. After you allocate, you need to rewire the list to still be in order, which will probably require iterating through the whole thing. And then you can go the way of the buddy system. Now, this is extensively explained here, but I'll just give you the idea of it. It's a way of organizing memory based on a formula that you know already, that allows you to split and re-coalesce memory easily in a really nice way. So here is the story. You know that 2 to the n equals 2 to the n minus 1 plus 2 to n minus 2 plus so on plus 2 to the second plus 2 plus 1 plus 1. You might know this better as 2 to the n minus 1, right? You may know this as such, right? But it's the same thing. So the trick here is that, and there is this game, you most likely played it on your mobile. I think it's called 2048. Two neighboring 2s will make a 4, and then that 4 with a neighboring 4 will make an 8, and so on. This is pretty much the idea here. Suppose we organize our memory in chunks that are powers of 2. So we will have several lists. A list that contains free memory of size, let's say 64. List that's with free memory of size 32. A list with free memory chunks of size 128, and so on. So we organize initially, because memory size is power of 2, we'll have just one list with the largest chunks. Maybe it will be just one chunk. The trick is that when we allocate, oh, really? It was? Awesome. I didn't know that. So when we allocate, let's say somebody asks for 13, we always choose the chunk that best fits our request. So if they want 13, we will provide 16, right? But if we can find 16, we'll find the smallest chunk available. So let's say that will be actually a 64. But when we allocate the 64, what we do, we split it as follows. So we take 16 out of it, and the remaining 16 and 32 we distribute to the other lists. So now the 64 became a 16 occupied, and the 16 and the 32 that are free. So this makes finding the free spot that matches us really easy. And the beautiful part is that when you free this allocated memory, right, when you free the 13, you'll actually free the 16. And if its body 16 is still free, they will make together a 32. And if this 32 is still free, they will make together a 64. So you practically coalesce RAM back together to large chunks really easily. I will let you read the details from the book, but this is the gist of it. So with this, I'm going to move to the last part of memory management, and that will have to do with caches. So let's see what the whole story with caches is. And I will start the story about caches, which is basically, let me make sure I'm not skipping anything. No, I'm done. This is right at the end of this document. Oops, too much here. So let's start the story about caches with mechanisms for storing data in a computer. And I will start with the largest and also the slowest one, which is the hard drive. So we will have the hard drive, or nowadays the solid state, which is going to be largest, and it's also going to be the slowest. And now I want to go at the other end of the spectrum and put the mechanism that is smallest, but also fastest. Anybody can suggest which one this is? What is the smallest place where you can store data in a computer, but it's really fast? No, no, no. Go. Even RAM is in the middle. L1 cache is almost there. Go one level higher. You've used them. How about the registry? The registers, sorry, the registers. So registers are kind of small, but they are very fast. That's why you get your values in them and do calculations. All right. Now, this whole thing is very simple. You need to use data. And if you need data, it's really optimal to bring it close to where you're using it. I'm going to make an analogy now. If you want to eat an apple, you'll go to the supermarket, but you'll not just buy one apple, because probably tonight or tomorrow you'll want another one, and you don't want to go to the supermarket again to buy an apple. You'll buy a bunch of them. You're going to cache your apples in your home. So practically, if you think of it, there is always a hierarchy of caches. If we're looking at the computer, you don't want to have to work with a hard drive. Working with a hard drive from the perspective of a processor is like planting a tree if you want an apple. If you want an apple, okay, you go, you dig the hole, you put the tree, you wait for it to grow, make apples, and then you eat it. You don't want that. So you have caches. So the next level above the hard drive is the RAM, which is smaller, but is also faster than the hard drive. And then you'll notice, if you read the specs of your processor, that they will have a number of caches, such as L1, and there will be an L2, and depending on your case, there will also be an L3. So it's really a hierarchy of caches. So this is the tree, okay? This is the supermarket. This is your cupboard, this is your fridge, this is your lunch bag, and this is your hand, right? You can think of it like that. If you search Google for processor picture, and you get the a microscope photo of a processor, there are good chances that you'll find it annotated. And you'll see that registers are really close to the processing unit. And L1 is not as close as the registers, but still close. L2 will be a little farther and a little larger. L3 may not even be on chip, may be off chip, but still larger. So actually caches are physically closer or farther from the CPU. We have here actually a hierarchy, which at the top is really small but really fast, and at the bottom is really large but really slow. So in back long years, you may have had an L1, and then slowly they figure out, you know what, an L2 will help, and then an L3. So this hierarchy of caches keeps improving. I don't know if there is anything beyond that, beyond an L3. But at this end, Before the SSDs were so common, the technology was really expensive. You would get hybrid hard drives, which would have the most of the storage would be HDD, but they would have a little bit of flash, like 8 gigabytes on a 1 terabyte hard drive. And the hard drive would know how to migrate popular data to this flash, practically caching it a little closer to whomever is asking. So this caching business is really popular and very, very useful. Now, the aspect that I want to talk about caching is how do you put data in cache? Where do you put it? How do you find it back? And let's just talk maybe RAM and L1. Okay, ignore the others. So you have a cache and you have the main memory. Exchanges are done by pages. So the CPU wants a page, you bring it in cache. So the cache, let's say the cache will have 16 pages. Not necessarily a realistic number, but if we consider the RAM having 1,000, then you kind of see. Oh, there is an L4, thank you. You kind of see that the cache is much smaller than the RAM. So when the processor needs a page, let's say the processor needs page 37 from the memory. Where do you put it in cache? There are two problems here when you choose how to do this. You need to put it in a way that you can easily figure out that you already have it in cache, right? And you also need to put it so that you can easily find where to put it. So the easiest way to do it is to use the so-called direct cache. And given a cache size C and the page P, the position in cache would be P modulo C. So in our case, if you want page 37 and you want to place it in a cache of 16 positions, you're going to place it on 37 modulo 16, which I believe it's 5. Right? So this is really easy. Very easy to figure out if you have. If you have a page in your cache, you simply calculate its position, you check if the page number is what you expect, and you use it. If not, you have to write the cache page back to memory and bring the one that you need. And this is the problem. So let me just, this actually creates a problem which is called collision, which can lead to thrashing. So here, page 37 modulo 16 would actually be on position 5 in our cache. But if our process needs the following sequence of pages, all these pages will go to the same position in cache, position 5. So this is a collision, it's cache collision. Two different pages need to sit on the same spot. So what do you do? In this case, caching stops being useful and actually starts slowing things down, because if you have a cache collision, you have to write back to memory the page that is in cache and bring from memory the one that you need. And if you keep doing this with two pages on and off, things will be extremely slow. So what we're actually going to talk about here, you probably have seen already, is what people use for hashing, for hash maps. And modulo is just a little function for hashing, but it has a high collision rate. So now if you want to solve this, the first choice, or the simplest choice, would be to jump to the other end of the spectrum, to say, you know what, no hashing at all. I'm just going to use an associative cache, which means I will simply iterate through the cache pages till I find a free one and then place my page there. And if I want to know if a page is in the cache, I'll just iterate through the cache pages and figure out if it's there. So this is much slower. You cannot figure out directly where to put the page. You cannot figure out directly where the page is. You have to search for it. But the collisions will be really much less. So then, as always, the best solution is a compromise, is somewhere in the middle. So we're going for a cache that is set associative, meaning that instead of using modulo to determine the exact page cache position where the page should go, we use modulo to determine a group of pages, a group of cache positions where the page should go, and then within that group we will search for a free position. So in a cache set, you may have the 16, you may organize it in, let's say, 4 sets of 4 pages, right? In which case, page 17 would go into set, sorry, page 37 would go into set 37 modulo 4, which is set 1. And then within the set 1, which has 4 pages, you will iterate and find where to place your page. Not as fast as direct cache, but much less collisions, because now you can have 4 pages in the same set, and the chances that you will end up thrashing a whole set are much lower. So if you guys have questions about this, please come up with them now. All right, maybe I'll move on then, because this is not exactly complicated, so probably you all have questions. And I'm going to switch to file systems. Now, here I will talk mostly about the Unix file system. And I'm practically moving to the last part of the theory that we're talking about. First was, what do you do with processes? How do you process them? Scheduling, what are their states? Then it was memory management. How do you deal with memory? And now the question is, how do we deal with the disk? How do we do a file system? And when we talk about the file system, initially it's all about files and maybe directories. But you will see that the Linux file system is actually quite extended, and it contains more than just these 2 files, these 2 types of files. But I will start with those. And just to have an overview, let's see of what types of files can we have on the Linux disk. But obviously, you have the normal files, like source code files or documents or movies or photographs or whatever, pictures, right? These are the normal files. Now, these are usually grouped in directories. Now, a directory is actually still a file, but it's a special file that contains the list of its children. That's it. So it's a special file, but still a file. You still need to live on disk. Then you have links. Now, these ones I didn't talk about. Symbolic links I did. So these are, if you want, if your file system is a tree, right? Directories and children and so on, the links make it into a graph. You can have in a directory a link to a file or another directory that's somewhere else. Why would you do that? Well, maybe you use very often a directory which has a really ugly path, or a file that has a really ugly name. You can just make a symlink with a simple name for it and use it easier. This is, let's say, one reason. And this would be the symbolic links. The hard links, I'll get to them a little later. So for now, let's just stay with the symbolic links. You may associate them with what you are used to as shortcuts in Windows. Yes, Perlmonkers, thank you, but they're not really shortcuts. The shortcuts in Windows are little files that react to your clicking on them. Double click a shortcut and it opens what you need. But if you try to open a shortcut in an editor, it's not going to open the file behind it, it's just going to open the shortcut itself. So when I say symbolic link, I mean a true alias for a file or a directory. And you can use the symbolic link as if it were the same file or directory. In Windows, you have this also. They appeared, I think, in Windows 7 for the first time. You can create them with a command that's called mklink. Well, shortcuts don't always need to point directly to the executable. You can have in Windows shortcuts that point to directories or to files. It's just that they react to click. You can create a shortcut to a document. But symbolic links are true aliases. So mklink in Windows will create them. In Linux, it will be ln-s. And then you can have other types of files. You can have, you've seen FIFOs already, right? Kind of like pointers to variables. But it's really easy. Let me demonstrate. Maybe this will help. This is not really the largest font, but I think we'll survive. So let's say echo ASDF into a file. And the file is going to be called ABC. So cat ABC will show us ASDF, right? So now let's create a link, but I need to, I don't know by heart the order. It's target and then link. So let's do this, ln-s. We need to put s to make it symbolic. Hard links are only for the root user. You'll get why a little later. And now we're gonna say, we're gonna make a link towards ABC and we're gonna call it DEF. Okay, so now if I say cat DEF, it's gonna show me the content of ABC. If I say echo 1, 2, 3 at the end of DEF, if you look at ABC, it's gonna contain it. So it's a true alias, right? If I do an ls-l, oh god, there is too much stuff here. Let's say ls-l, ABC, and DEF, then you can see that DEF is actually a symbolic link to ABC. So you may think of them as pointers, they're really aliases, and you'll understand what's behind them really soon, in about half hour. Okay, and then you can have other types of files. For instance, if you attach a tape drive to your computer, then you'd have one of this. You'll have a block device. You may have character devices. These are very rare nowadays. And then you also have these types of files, which are specific to Linux. They're represented as files. And they are still handled by the operating system. So this is what the Linux file system holds. But our goal is to try to figure out how would we store on a disk these two, and then we'll also look at what's specific to Linux. So we're kind of gonna build up what Linux has. So a disk is really a large storage area in which you have to put data. The problem is very similar to what we've just talked about for malloc. Is quite the same thing. You need data. You need to put data on disk. So you need to malloc to allocate space on disk. But you don't say malloc, you just write it. However, the operating system behind the scenes needs to know what's free and what's not free. where to put it, and so on. All right. Now, a file will never sit on disk contiguously because that would just not work. The file will always be split into blocks, and you're going to place the blocks on disk wherever you can, quite similar to what you do with memory page allocation as a concept. You split it and you put blocks wherever you need. Blocks would be probably about 8 kilo in size nowadays. But if you do that, then you'd have to have a way of keeping track of what blocks belong to what file. You'll need to have some kind of entry point to a file from where you can reach all its files. Now, depending on the file system that you're using, this structure will differ. The most common file system, I guess, I haven't checked statistics, but I would say FAT is still the most common because you're going to find it on all USB sticks. It's really simple, actually not secure at all, and that's what makes it attractive because you can plug it into any computer. You're not going to bump into security issues, ownership and stuff, but easily corruptible. FAT handles this file entry points rather like a linked list, but it's not exactly performant. What we're going to look at is an idea that is a little more complicated. It's specific to the ext2 and 3 Linux file systems, but most of them have these concepts behind them, although the organization may not be the same. So here is how we store things on disk in terms of files and directories. So let's start with the files. How do we know the blocks of a file? Now the material here is organized oh, you use X4 on your USBs? Right, can you plug them into Windows then? And Macs? Will they be seen? I never really tried that. So the material here is organized differently than I'm teaching it, but that's just because I have to compress stuff as much as I can to fit into these hours that we have. So I'm gonna, and there is a lot more stuff here about file locking and such, which I'm not covering. So let's just go to a little lower to the notion of Inode. Okay. So this is an Inode. Let me tell you what that actually means. So this is how Linux keeps track of the blocks of a file. It has this structure, which has an initial part about with identification data. We'll see it later. And then there are a bunch of pointers toward data blocks. The circles are the data blocks. And the structure is somewhat optimized to work fast for small files, because the majority of files on a system are not that large. So you want to have those working as fast as possible, and then the others, which are not as frequent, you don't need to optimize so much. So here we are giving this example, and I will ask you to read it, but I'm just going to go with blocks of 8 kilobytes. Okay. So what we do here is in an inode, we will start with, let's say, 10 pointers to blocks of data. So if the file is really small, it will fit in the first block of data, and the rest will be blank. If the file grows beyond our block size of 8 kilo, goes to 10 kilobytes, then we will allocate another block. So to find these blocks will have to go to the second pointer. So the file can go up to 80 kilos, and we're just gonna allocate another block which is accessible directly, right? Directly from the inode. However, if the file goes beyond 80 kilos, or maybe if I were to speak generically, beyond 10 blocks, then we do a so-called indirection. We'll have a pointer to a block that contains pointers to data blocks. So now we can grow exponentially. Now in a block, the number of addresses will be the size of the block divided by the size of the address. Here we're looking at blocks of 512 and addresses of 4 bytes. That's why you have 128. But these numbers really depend on the size of the block and the size of the address. So now the size of the file size grew significantly, but it requires an extra access to find it. Now, if the file goes beyond this, then we do a double indirect, which takes this pointer goes to a block which contains pointers to other blocks, and those blocks in turn point to data blocks. All right, and then if this is not enough either, then we go to triple indirection, but this has an extra level which it shouldn't. It's the image has a problem. We would have 3 levels, so one of this is extra. This one, I would say. So this is how you keep track of what blocks you have. And the larger the file, then the blocks require a few more accesses to get to them. But most of the files being small will fit into the simple indirection, or maybe a little bit of the double. So this is one way of keeping track of your data on disk. If you go to FAT, they will have a linked list. If you go to NTFS, they'll have a completely different structure. Now, the next question is, all right, so we know that every file will be split into blocks. The blocks will sit somewhere on disk, and we will have this index, which is called an inode, that gives us access to the blocks files. But how do we organize files into directories? Well, directories are still files, but their content is a list of children. So here is what a directory contains. A directory contains a list of pairs, file name, and inode ID. So these inodes are stored in an area, which I should have started with, but I'll go back to it now. These inodes have identifiers. So your directory entry is name and inode ID. And if you have a subdirectory, that will still be a file. It will still have an inode, so you'll have the name of the subdirectory and its inode ID. Now, the inode itself in the identification area will contain a bunch of things itself, but you notice it doesn't contain its name. The inode is the entry point to the file's data, which is separate really from the name of the file. So the inode, okay, Water Addict is asking if a file can fit into more than, no. A file will, a file's data will have to fit in an inode. However, a file may have several inodes, but they will not contain the same things. I will, if I don't forget, I'll get back to this, but what I'm talking mostly here is ACLs right now. Access control lists. I'll get back to you. So an inode will store the type of the file and its access. It's what ls-l shows you, the type of the file, the little character at the beginning, and then the read, write, execute triplets. Right? That's in the inode. And it will have its owner and its group, right? The owners as user and group. What's the size, access time, and then these are the links to data. So this is the content of an inode. This is the identification part. So then our directory hierarchy is really files containing names and inode IDs of other files. And if a directory gets really large, it will probably have to spill in more than one block. You may have noticed, but maybe not yet, that people prefer to have small directories. People try to avoid directories with thousands of entries because they become really slow. Just to list them takes a lot. Some operating systems are optimized to make even this case fast, but it's not really always necessary. Usually people, if they have directories with lots of things, they will find ways of splitting them into subdirectories just so that the directory doesn't have more than so many entries, which can cripple the performance on certain file systems. So now we have directories and we have their content, inodes. How are these gonna sit on the disk? Well, there are many ways of doing it, but here is the structure of the Unix disk. This would be an ext2, for instance. The first block on the disk is usually the booting block. That's used for booting the operating system. The next block is the so-called super block. It contains data about your disk. These are details about how the disk is organized. Then you'll have an area where you keep inodes. So when I say inode ID is literally the index of the inode in this area. And then the largest part of the disk is the data. So whenever you create a file, you occupy an inode here and some data blocks here. It is possible, if you have loads and loads of small files, to run out of inode space, although you may have enough data space. Usually it's the other way around. You run out of this and not out of this. So again, this is similar to what I think Aurelia suggested when we talked about malloc. Let's have an external structure or something to keep track of what's free and what's occupied. This is exactly what the disk does. Allocates an area where you keep the accounting and an area where you keep the data. For memory allocation, we chose to mix them as links. But when you work with the disk, this is better. Questions if you have up to this point. So now, to answer Water Addict's question, yeah, nice. About several inodes per file. You'll find this also in Windows. Windows will call them, I believe, streams. A file may have multiple streams. So every file will have a main content, which in our case is the primary inode, and in Windows would be the primary, on NTFS would be the primary stream. That's where you put the file data. However, a file may have other data associated with it. This wasn't the case before. However, at the point, these permissions on a file became insufficient. It was not enough. It was not flexible enough to just grant permissions to a group of users. You sometimes needed a file to have different permissions for different groups or different permissions for different users. And the size of this permission data is not really fixed. You may want to give different permissions to 100 users or maybe to one. So whereas these permissions that we use today are really fixed, they fit into 9 bytes, 9 bits. Actually, extensive permissions can have any size. And these are called access control lists. You can find them in Windows. In Windows, they're very visible. If you go to permissions, you can choose which user has what permissions. In Linux, you need to use a command called, I think it's getfacl. ACL is access control list, so it's something about file access control list. Set AFCL, get AFCL. Okay, so where do you store that data? Where do you store that potentially massive amount of access specifications. Never mind that using these ACLs too much